Okay, picture this. You're trying to map out the most efficient way to run your weekend errands. Or maybe you're wrestling with organizing, like a huge digital photo library.
Oh, yeah.
Or perhaps even planning the logistics for a complex work project.
Yeah.
These tasks can feel overwhelming,
Oh,
right?
totally.
You instinctively want to solve them as efficiently as possible, but how do you even begin to break them down?
It's true. Those everyday challenges, when you look closely, they often involve elements of, defining steps, applying logical rules,
Hmm.
figuring out the sheer number of possibilities, and managing finite resources like time or space.
Right.
And that, surprisingly, puts us squarely in the realm of computer science.
Exactly. And today we're taking a deep dive not just into writing code, but into the fundamental mindset and toolbox that underlies effective problem solving, whether you're using a computer or just using your brain.
Yeah.
Our source material for this exploration is the book Computer Science Distilled: Learn the Art of Solving Computational Problems by Władysław Viana Ferreira-Fia.
And the book makes its purpose very clear right from the start. Its goal is to teach you the art of solving computational problems.
Oh.
It's absolutely relevant if you want to use computers and programming effectively, efficiently, but it presents these core computer science concepts in what it calls plain distilled forms, focusing on building computational thinking.
And I love that it's not aimed exclusively at, computer science majors or seasoned developers.
Right.
The book is really intended for everyone who faces problems and wants to smash problems with efficient solutions.
Hmm.
You don't need a ton of programming experience, just maybe recognizing what a basic loop is. But for those who've experienced, it also serves as a really solid foundational recap.
Definitely. Our mission in this deep dive is to unpack the core ideas from the book's foundational chapters, the first two, basics and complexity.
Right at the start.
Exactly. By exploring these, we aim to equip you with a powerful toolbox for problem solving that you can use anywhere, and critically, to build an understanding of why efficiency isn't just some technical detail for programmers.
Like an afterthought.
Yeah, but a fundamental concern in dealing with problems at scale.
Okay, just a quick note on the book itself. The author is Władysław Viana Ferreira Filho. It was published by Code Energy LLC, first edition back in February 2018.
Mm-hmm.
The sources even mention a dedication to friends who encouraged him to finish, which just reinforces that this came from like a desire to share this foundational knowledge.
And the author's core message, woven throughout the book, is that computer science knowledge is truly essential for effective programming and for really pushing machines to their full potential.
Yeah.
This perspective is particularly relevant today, where raw computing power is, well, abundant.
Everywhere.
Right. But the ability of people to wield that power effectively to solve complex problems is actually quite scarce.
It's worth noting, too, that the book goes much deeper than just these first two chapters. It covers strategy, data, algorithms, databases, computers, and programming.
Mm-hmm.
It really provides a comprehensive foundation.
Oh, absolutely. It's a whole journey. But for today, we're starting right at the beginning.
Makes sense.
You can't build a house without a strong foundation, right?
Right.
And for computational thinking, that foundation is in the basics.
Okay, let's dive into that first chapter, Basics. The book presents this as your essential problem-solving toolbox.
Right. Think of this chapter as giving you the fundamental mathematical and logical concepts you need before you even start thinking about writing code.
Okay?
The goal, as the book puts it, is to help you break down problems into chunks that computers can process and, critically, to translate ideas into computable solutions.
Now, the book is upfront.
Mm-hmm.
Yes, there's math involved.
Mm-hmm.
But the way it's presented is really practical. It focuses on the tools you need to model and analyze problems rather than requiring, advanced theoretical knowledge.
Exactly. It's about using math as a language to describe problems precisely.
Got it.
Absolutely. The chapter divides this toolbox into 4 key areas. The first is ideas, which is all about how you approach modeling problems and the absolute necessity of externalizing your thoughts, getting them out of your head and down onto paper or a screen.
Which, frankly, is something everyone can benefit from, programmer or not. Our working memory is so limited.
Exactly. We can only juggle so much in our heads. And the book gives us a couple of powerful tools for this. The first one, flowcharts.
Ah, the classic boxes and diamonds, like building blocks for processes. Takes me back.
Yeah. Their fundamental purpose is to represent processes visually, step by step. The sources offer great examples like a flowchart showing the agreed-upon process for Wikipedians editing articles.
Oh, interesting.
Visualizing the steps actually helped them resolve a debate they were having about the process.
Huh.
There's also a very clear flowchart for finding the maximum of 3 numbers, which is, a common early programming logic problem.
And the book provides practical guidelines for drawing them effectively. Use rectangles for actions or steps. Diamonds for decisions, those questions with yes-no answers.
Right, the branches.
Don't mix these shapes, connect everything with arrows showing the direction of flow, and clearly mark the start and end points.
Yeah, clear start, clear end.
Yeah.
It also briefly mentions UML, the Unified Modeling Language, as a more standardized way to do this in software engineering, kind of the next level up.
Sure.
And think about how this connects to you, the listener. Whenever you're trying to explain a process, whether it's how to handle a customer complaint, how to assemble that piece of IKEA furniture,
Always a challenge.
or even just your morning routine, drawing it out as a flowchart can reveal hidden steps, potential bottlenecks, or points where decisions need to be made. It brings tremendous clarity.
That makes a lot of sense. Okay, so once you have the flow visualized, the next tool under ideas is pseudocode.
Right. Pseudocode is like the next step towards actual code. It's about drafting the logic of a programmable process in a way that humans can easily read and understand.
But crucially,
The key thing here is that it completely ignores the strict rules, the syntax of any specific programming language.
so it's not code that a computer can run directly.
Nope.
But it uses a structure that looks like code, maybe combined with plain English descriptions of the steps.
Precisely. The book provides pseudocode for that same maximum function we mentioned. You might see lines like read number 1, number 2, number 3, then maybe max number 1.
What's that arrow?
Good question. The lady here is the assignment operator. It basically means set the variable on the left to the value of the right. So max number 1 means set the variable max to whatever value number 1 holds.
Okay, like an equal sign in math, but specifically for assignment.
Exactly. Then you'd see maybe if number 2 max, then maxing number 2, at number 3 max, then max number 3, and finally write max.
So it's like writing a detailed recipe for the computer, but using your own language and common programming ideas like statements and assignments.
That's a great analogy. And the book really encourages letting your creativity flow here. Just like with flowcharts, you're capturing the logic and the sequence of operations first,
Yeah.
without getting bogged down in whether you need a semicolon here or parentheses there, which would be required in actual programming languages like, say, C++ or Python or Java.
Nail down the idea first, worry about the grammar later.
Exactly.
Okay, and the third tool in the ideas section is mathematical models.
This is where you represent the problem using established mathematical concepts and then apply relevant mathematical techniques that are already known to solve that type of model.
So leveraging existing math knowledge.
Pretty much. It's standing, as the saying goes, on the shoulders of giants. If your problem involves relationships between points and connections, maybe graph theory is the tool. If it involves optimizing a quantity under constraints, maybe algebra or calculus is needed.
The source uses a really relatable example from, honestly, high school math, the livestock fence problem.
Yes, the classic optimization problem.
You have 100 units of barbed wire, and you need to build a rectangular enclosure that's divided down the middle by one straight segment of fence parallel to one pair of sides.
Okay.
You want to use all 100 units of wire and maximize the enclosed area. How do you model that?
Okay, let's break it down. Let the width of the rectangle be W and the length be L. The area we want to maximize, let's call it A, is simply WL. That's the goal.
Right, area width times length.
Now let's look at the wire constraint. You have 100 units total. If the division, that middle fence, is parallel to the width side, let's picture that. You'll have 2 sides of length L, the top and bottom, and 3 segments of length W, the 2 ends plus that middle division.
Right, 3 widths, okay.
So the total wire used is 2L plus 3W, and this must equal 100. So our 2 equations are AUWL, and 100 equals 2L plus 3W.
All right, so we have 2 variables, W and L, but we want to express the area A using just one variable so we can find its maximum. We need to substitute.
Exactly. Let's rearrange the second equation to solve for L. So 2L equals 103W. Divide by 2, L is 50, 32W. Or 50 minus 1.5W.
Okay, got the length in terms of width.
Perfect. Now substitute that expression for L back into the area equation. A equals W, 50, 32W.
Right.
Expanding that out, multiply the W through. A equals 50W, 32W.
And bingo. The book points out this is a quadratic equation.
Yes.
So-
Specifically of the form x2 plus bx plus c, although here our variable is W. It's a, now it's 32 plus 50w plus 0. The coefficient of the squared term, a, is negative -32.
Which means the parabola opens downwards, it has a maximum point.
Exactly. And the profound insight here is that once you've modeled your real-world problem building a fence to maximize area and it results in a quadratic equation, you don't have to reinvent the wheel.
Yeah.
There are established mathematical techniques, like finding the vertex using the formula B2A or using basic calculus, specifically designed to find the maximum or minimum value of a quadratic equation quickly and precisely.
So the power of mathematical modeling isn't necessarily about being a math whiz who can solve anything on the fly, though that helps.
Yeah.
It's more about recognizing the shape of your problem. Like, oh, this looks like a maximization problem that turned into a quadratic equation. And knowing that there are existing proven tools, math techniques available to solve that specific shape of problem efficiently. It's about having the right tool for the job you've just modeled.
That's perfectly put, which brings us nicely to the second section of the basics chapter, logic, which is subtitled Knowing Right from Wrong.
This feels fundamental. The book emphasizes that formal logic is used by coders constantly, even if they don't realize they're doing it.
Oh, all the time. It's statements, while loops.
Learning it deliberately allows you to be much more precise and effective.
Definitely. It starts with the most basic building blocks, logical variables. These are statements that can only ever be one of two things, true or false, period.
Like the examples given. A, the pool is warm, or B, I will swim. On any given day, each statement is either definitively true or definitively false. There's no maybe.
Right. Then it introduces the core logical operators that combine these variables. The conditional, which means if A, then B.
If A is true, B must be true.
Negation, meaning not A. The biconditional, meaning A if and only if B.
They have to be true or false together.
Exactly. And the more familiar ones from everyday language, AND or an XOR, exclusive OR.
Right.
The examples make them pretty clear. If the pool is warm, I'll swim is AEB.
Okay.
A means the pool is not warm or the pool is cold.
Simple enough.
I'll swim if and only if the pool is warm is AEB. Both conditions must match.
And the classic party example.
Yeah.
If someone asks if you want vodka and wine, you need both.
Yep. Got it, both.
If they ask for vodka or wine, you can have either or even both.
Inclusive OR, yeah.
If they ask for vodka XOR wine, you can have one, but not both. Exclusive OR.
Precisely. One or the other, not both, not neither.
A key concept the book highlights is the contrapositive. A conditional statement, if A, then B, AB, is logically equivalent to if not B, then not A, B, A.
Right. This is super useful. So the statement is, if the pool is warm, I'll swim. The contrapositive is, if I didn't swim, the pool isn't warm. These two statements mean exactly the same thing, logically.
Okay.
The book uses another example. If you can't write good code, you haven't read this book is equivalent to its contrapositive. If you read this book, you can write good code. Same logical structure.
And there's a crucial warning against the common inverse error. AB does not mean BA.
Oh, absolutely not. This trips people up. Just because I swim if the pool is warm, AB, doesn't mean the only condition under which I swim is if the pool is warm, BA. Maybe I swim in cold pools too. Conflating these is a major logical fallacy.
Got it. The arrow only goes one way unless it's the biconditional.
Exactly. Beyond just understanding these operations, the chapter introduces Boolean algebra. Think of it as a set of rules, like regular algebra, but specifically for simplifying logical expressions.
Okay.
It uses rules like associativity, distributivity, and the famous De Morgan's laws.
De Morgan's laws are powerful. For example, saying it's not the case that both A and DB are true. So A and DB is the same as saying either A is not true or B is not true. So A and DB kills A or B.
And the other one is A or B, ADB, saying it's not the case that A or B is true is the same as saying A is not true and B is not true.
And the book gives a nice nod to history here, mentioning George Boole, who founded the field of symbolic logic, and that Augustus de Morgan was friends with Boole and even tutored Ada Lovelace, often considered the first computer programmer. It brings the concepts to life a bit.
It does. It shows the lineage. The book then uses the hot server problem to demonstrate the power of Boolean algebra for analysis.
Okay, let's break this one down. The server crashes. Let's call that outcome D. If it's overheating A and D, the AC is off B or R, the chassis cooler fails. C.
Right. So the condition for crashing is A and D, B, O, or C. That whole thing leads to D. So A and D, B, O, or C, A, D.
Okay, A and B or C.
Wait, the source says server crashes if overheating A and D, AC off, or chassis cooler fails. Let me reread that condition carefully. It's formulated slightly differently in the source notes, implies distributivity was already applied, A and D B, or A and D, AD, overheating AC off, or overheating AD cooler fail. Okay, let's work with that. A and D, or A and DC is the crash condition.
Okay, A and D B or A and D C. That looks like distributivity in regular algebra, right? Like
Yeah.
xi plus xz, xy plus z.
Exactly. We can factor out the A and D. So A and D, B, or C. That simplifies the crash condition. So the server crashes if it's overheating A and D. Either the AC is off or R, the cooler failed.
Okay, so the condition for crashing is A and D, B, or C.
Yeah.
Now we want to know when the server works, which is the opposite.
Right. If the condition A and D, B, or C, implies D crashing, then by the contrapositive rule, D working implies the negation of the condition. A and D, B, or C.
So the working condition is A and D, B, or C. How do we simplify that?
Now we use De Morgan's laws. The first law is do A and D Y, X or Y. Here X is A and Y is B, O, or C.
Okay.
So applying that, A and D, B, or C becomes A or R, B, O, or C.
Got it. Not A or not B or C.
Now we apply the other De Morgan's law to the second part. B, O, or C. B, A, and D, C.
Right. The negation of an OR is the AND of the negations.
Putting it all together, the working condition for the server simplifies to A or R, B, and D, C.
Okay. So just using logic and Boolean algebra, we've transformed a seemingly complex set of failure conditions into a clear statement of when the system works. Either the server is not overheating, like A or R, both the AC is not off, and the chassis cooler is not failing.
Exactly. That's a much clearer picture of what needs to happen for things to be okay. It's a powerful simplification that helps you understand exactly what conditions are necessary for the system's success.
It really is. Another vital tool for analyzing logical models is truth tables.
The brute force method, in a way.
This is where you methodically list out every single possible combination of true-false values for your logical variable.
Exactly. You make a table. Each logical variable gets its own column. Then, for each possible combination of true and false values for those variables, you create a row.
How many rows does that end up being?
Well, if you have one variable, there are two possibilities, true or false. With two variables, it's T, TF, FT, FF. That's 2, 32, or 4 rows. With 3 variables, 222 or 8 rows. With n variables, you have 2n rows. The book notes this leads to a size explosion very quickly. 10 variables means another town is 24 rows. 20 variables is over 1 million rows.
So useful, but maybe not for super complex systems with tons of variables.
Right. But for understanding smaller sets of conditions, it's incredibly thorough. The book uses the fragile system problem to show this. There are 4 requirements for a database system. Let's call them A, B, C, D, all involving conditions like whether the database is locked, the queue is full, or the cache is loaded. For example, one requirement might be if locked A, then you can save B, so A, B. Another might be lock A cannot happen when the queue is full. C may be represented as A, and D, C. There are 4 such rules.
So with 4 variables, A, B, C, D, you'd need 24 equals 16 rows in your truth table.
Correct. You list out all 16 possible true-false states for A, B, C, and D. Then, for each state, each row, you check if all 4 requirements are simultaneously true in that state.
So you evaluate each rule for that rows combination of TF values.
Exactly. By methodically going through every single possibility, the truth table systematically reveals if there are any states where all requirements are met, and if so, what those states are.
And for this particular problem, the book says, after filling out the table,
You'd find that the requirements are only met in states where the variable representing database locked, A, is false. The profound insight gained from the truth table analysis is that based on these requirements, the database can never be locked. The rules contradict each other in a way that prevents A from ever being true if all rules are to hold.
that's a huge finding, something you might totally miss just trying to reason about it informally.
Exactly. That systematic, exhaustive checking is the power of truth tables for complex logic.
And perhaps the most impressive application of logic, as the book highlights, is its role in the design of electronic computers themselves.
This is where it gets really cool, yeah.
Here's where it gets really interesting. Those true-false logical variables. They directly map to the binary number system computers use. True is 1, false is 0.
The foundation of digital systems. And the logical operations, AND or XOR, directly correspond to basic calculations on these binary digits or bits.
And this is implemented physically using logic gates.
Right. These are simple electrical circuits that perform basic logic operations like AND, OR, and XOR. True and false are represented by different voltage levels. Maybe high voltage for true 1, low voltage for false.
Okay.
By connecting millions or even billions of these tiny logic gates together in clever ways, you create complex circuits that can perform incredibly sophisticated calculations almost instantaneously.
Billions in a modern CPU.
Yeah.
Okay.
Easily. The book shows a figure of a simple circuit that sums two 2-bit binary numbers using just XOR and AND gates. It even walks you through adding 2 plus 3 in binary.
Okay, let's try to walk through that binary addition verbally. 2 binary is 10, 3 in binary is 11. So we're adding 10 plus 11.
Right. 2 bits each. Let's add the rightmost bits first, 0 and 1.
Okay, 0 plus 1.
The XOR gate output for 0 XOR 1 is 1. This gives us the rightmost digit of the sum.
Okay, sum is 1.
The AND gate output for 0 AND 1 is 0. This is the carry bit to the next position, the next column to the left.
Okay, carry is 0. Now the left column, we have 1 and 1.
Right. Now move to the leftmost bits. 1 and 1 plus the carry, which was 0 from the previous step.
Wait, 1 plus 1 plus 0.
You typically do this in steps with gates. Maybe XOR 1 and 1 first, which gives 0.
Right.
Then XOR that result 0 with the carry. 0 XOR 0 is 0. This gives us the next digit of the sum, the second digit from the right.
Okay, so the sum so far is arrow 1, reading right to left. Now what about the carry for this position?
Good question. You need AND gates too. You'd AND the original inputs, 1 AND 1, which is 1. You might also need to consider the carry-in. A full adder circuit handles this properly. The book's diagram shows the result. The essential idea is combining XOR for the sum bit and AND, plus some ORs maybe, for the carry-out bit.
So for 1 plus 1 plus carry is 0, the sum bit is 0. What's the carry out?
The carry-out for 1 plus 1 plus 0 is 1. So we have a sum bit of 0 and a carry-out bit of 1.
Ah, so reading the result bits, we had the rightmost sum bit as 1, the next sum bit as 0, and now a final carry out of 1. Reading that left to right, it's 101.
Exactly. And 101 in binary is 4 plus 0 plus 1 equals 5. So the circuit correctly calculated 2 plus 3 equals 5 using only logic gates operating on binary representations.
That's incredible. So understanding logical operations like AND or XOR and truth tables helps you understand fundamentally how a computer performs arithmetic using electrical circuits.
It's built right on Boolean algebra, from bulky vacuum tubes in the early days to microscopic transistors packed onto chips now.
The core principle remains the same.
Exactly. That's a really powerful connection to make. Understanding logic is understanding computation at its root.
Wow. Okay, that covers logic. Let's move to the third section of the basics chapter, counting, subtitled, Getting the Numbers Right.
Counting might seem almost too simple, right? Like 1, 2, 3.
Yeah, basic stuff.
But the book shows it's absolutely essential for analyzing computational problems, especially when dealing with possibilities, combinations, arrangements. How many ways can something happen?
Right.
It's part of discrete mathematics alongside logic. The goal here isn't necessarily memorizing complex formulas, though the book provides them. It's more about building intuition. The formulas can always be looked up when you need them.
Okay, so what are the core tools?
The most basic tool is simple multiplication. The multiplication principle. If there are ways for one event to occur and m ways for another independent event to occur, there are num ways for both to occur.
Straightforward enough.
Like cracking a simple PIN code. Maybe it has 2 digits, 10 options each, 0, 9, followed by a letter, 26 options, AZ. The total number of possible PNs is 10. 10, 26 equals 2600.
Okay.
Or the team building example from the book. You have 23 candidates for a project. For each candidate, you flip a coin higher or don't hire. 2 outcomes.
So 2 choices for the first, 2 for the second.
All the way down. The total number of possible team configurations, including hiring nobody or everybody, is 2 multiplied by itself 23 times, or 223.
Which is large.
It's over 8 million. 8,388,608 possibilities, to be exact. Simple multiplication, but it quickly shows how the number of combinations can explode.
Okay, multiplication principle. What's next?
Next up are permutations, represented by n and factorial. This is the number of ways to order indistinct items.
Ah, factorial, where you multiply down.
Right. N is calculated by multiplying n by n1 by n2 all the way down to 1. So 5 is 5, 4, 3, 2, 1 equals 120. The book points out its explosive growth.
More explosive than the 2 and we just saw.
Oh, yes. Much faster growth for larger n. The classic traveling salesman problem is a great example. You need to find the shortest route that visits a list of cities exactly once and returns to the start. For just 15 cities, the number of possible orderings or routes is 15.
Which is?
Over a trillion, 1.3 trillion roughly. The book estimates that even a hypothetical super-fast computer checking 1 million routes per second would take about 15 days just to check them all.
Wow. For only 15 cities.
But here's the explosive part. Add just 5 more cities to make it 20. The number of routes jumps to 20.
Okay, how bad is that?
It's over 2.4 quintillion. That's 2.4 with 18 zeros after it. Checking that many routes would take that same fast computer over 77,000 years.
1,000 years. Okay, factorial growth is insane.
It absolutely is. It starkly illustrates why brute forcing problems involving permutations is often impossible.
So permutations are about ordering all n items. What if you're ordering just some of them?
Good question. That's also permutations, but of a subset. Like choosing and ordering 6 musical notes from 13 available notes for a melody. The formula is NM, where n is the total number of items, 13 notes, and m is the number you're choosing and ordering, 6 notes. So it's 13, 13 to 6 equals 13, 7. Still a large number, but less than 13.
Okay. And then there are permutations with identical items. What's that about?
That's when some of the items you're arranging are indistinguishable from each other, like the letters in the word Mississippi.
Lots of S's, I's, P's.
Exactly. If you just calculated 11, since there are 11 letters, you'd be overcounting because swapping, say, the first S with the second S gives you the same arrangement.
Right, looks identical.
So you have to divide the total permutations n by the factorial of the counts of each identical item. For Mississippi, it's 11, divided by 4 for the S's times 4 for the I's times 2 for the P's.
Okay, that adjusts for the duplicates.
The DNA example from the book is fascinating here. Consider a small segment of DNA, say 23 base pairs long, and suppose it's made up of 9 AT pairs and 14 GC pairs. First, how many ways can you arrange the types of pairs? AT versus GC. That's like arranging Mississippi. It's 23 total items with 9 of one type and 14 of another, so 23.
Right.
Ryan on 14.
Right, accounting for identical pair types.
But wait, there's more. Each AT pair can be oriented either AT or TA.
2 possibilities.
And each GC pair can be oriented GC or CG.
Also 2 possibilities.
Since there are 23 pairs in total, and each has 2 possible orientations, you have to multiply the previous result by 2, 23 times. That's 223.
So it's 23. 9, 14, 223.
Exactly. That calculation, the book notes, yields over 7 trillion distinct sequences for just that tiny 23 base pair segment.
For 23 pairs, wow.
And the book contrasts this with human DNA, which has about 3 billion base pairs. It gives you a sense of the mind-boggling combinatorial complexity inherent in biology built from these simple counting rules.
Incredible scale. Okay, so that's permutations. What are combinations?
Combinations come next. Represented by n choose m, often written as a tall parenthesis with n above m. This is the number of ways to select m items from a set of n items where the order does not matter.
Order doesn't matter. That's the key difference from permutations.
Precisely. Permutations are about ordered arrangements, like lining people up for a photo. Combinations are about unordered selections, like picking a committee. The formula is NM.
Okay, so it's related to the permutation formula, but divided by m as well to remove the ordering.
Exactly right. The chess queens problem is a combination example. How many ways can you place 8 queens on a 64-square chessboard? The specific squares you choose matter, but the order in which you place the 8 queens on those chosen squares doesn't change the final configuration.
So it's a selection of 8 squares out of 64.
Yep. That's 64 choose 8. You calculate 64 to 8, which simplifies to 64. That's still huge. About 4.4 billion possibilities. Fewer than 64, obviously, but still a massive number, illustrating why solving the 8 queens problem, placing them so none attack each other, isn't trivial by checking all combinations.
Got it. Permutations, order matters, combinations, selection only.
That's the core distinction. Finally, in counting, the book covers sums, using the capital sigma notation for sequential sums.
Right, summing up a series.
This is useful for problems where you're adding up a series of numbers that follow a pattern, like the sum of the first n natural numbers, 1 plus 2 plus 3 plus n.
And this is where the famous story of young Gauss comes in. The teacher gives the class a boring task.
Add up all the numbers from 1 to 100, and Gauss figures out a shortcut almost instantly. He realized you could pair the numbers. 1 plus 100, 101, 2 plus 99, 101, 3 plus 98, 101.
How many pairs?
50 pairs, each summing to 101. So 51, 101 equals 50. The general formula he derived is the sum of the first 10 natural numbers is n plus 1, 2.
A neat trick. The book mentions an appendix explains how he found it.
Yes, a little bonus for the curious.
The flying sheep example uses this idea. If you want to find all unique pairs of flight dates within a 30-day period, where the departure date must be on or before the return date, how does that become a sum?
Think about it. If the departure is day 1, there are 30 possible return days. Day 1, day 2, day 30.
Okay.
If the departure is day 2, there are 29 possible return days. Day 2, day 3, day 30.
Right, can't return before you leave.
Keep going. If the departure is day 29, there are 2 return days, 29, 30. If the departure is day 30, there's only 1 return day, day 30.
So the total number of pairs is 30 plus 29 plus 28 plus 8 plus 2 plus 1.
Exactly, which is the sum of the first 30 natural numbers, just written backwards. It's II from 1 to 30.
Ah, so we can use Gauss's trick, 30, 30 plus 1, 2.
Yep. 30, 31, 2 equals 932 equals 465 pairs of dates.
Nice. Much faster than listing them all out.
Definitely. The book also shows you could solve this using combinations. 30 choose 2 gives you the pairs with distinct dates, plus the 30 cases where the departure and return are on the same day. That also adds up to 465. Different ways to count the same thing.
Recognizing these summation patterns and knowing these clever formulas are another way computational thinking helps you find efficient solutions instead of just brute forcing it.
Exactly. It's about leveraging mathematical structure.
Okay, that covers counting. The final section of the basics chapter is probability, covering basic randomness.
Right. Because not everything is certain. Understanding probability helps us quantify uncertainty and make informed decisions when things aren't guaranteed.
And it's a concept often misunderstood intuitively, the book mentions.
Very much so. Our gut feelings about chance can be way off. The basic principle, though, for situations where all outcomes are equally likely is straightforward. The probability of an event, P event, is the number of favorable outcomes divided by the total number of possible outcomes.
Like rolling a fair 6-sided die. The probability of rolling a 4 is 1 favorable outcome, 6 possible outcomes.
16. Exactly. Or, going back to the team building example, with 23 candidates and 223 total outcomes, what's the probability of hiring nobody?
Well, there's only one way for that to happen. Everyone gets a no flip. So 1 favorable outcome.
Divided by the total 223 outcomes. So the probability is 1,388,608. Extremely unlikely.
Yeah. The book contrasts this tiny probability with something like the probability of an airline crash to give perspective.
Then we have independent events. This is crucial. 2 events are independent if the outcome of one has absolutely no influence on the outcome of the other.
Like flipping a coin and rolling a die, they don't affect each other.
Exactly. And if A and B are independent, the probability of both happening is PA, PB. You multiply the probabilities.
Okay.
The backing up data example from the book is a perfect illustration of why this matters. Suppose you have data and you need to back it up. Option 1. A single, super reliable, expensive disk with a 1 in a billion chance of failing over the next year.
Pretty reliable.
Option 2. Use 3 cheaper disks. Maybe each has a 1 in 2,000 chance of failing in the next year. Much less reliable individually.
Okay. Seems riskier.
But critically, assume these cheaper disks fail independently of each other. The failure of one doesn't make the others more likely to fail.
Right?
What's the chance of losing your data with option 2? That only happens if all 3 disks fail.
So we need disk 1 fails, disk 2 fails, and the disk 3 fails.
Because they're independent, we multiply the probabilities. P all fail. P disk 1 fails. P disk 3 fails. 12,000 fails.
3, that's 1 over. 2 times 2 is 4, times 2 is 8. 3 zeros cubed is 9 zeros, so 1 over 8 billion.
Exactly. 1 in 8 billion chance of total failure.
Wow. So using 3 cheaper, less reliable independent disks actually gives you a much lower probability of total data loss, 1 in 8 billion, than the single expensive, super reliable one, 1 in 1 billion.
That's the power of redundancy combined with the multiplication rule for independent events. It can be less risky and maybe cheaper.
That's a great insight. Okay, what about mutually exclusive events?
These are events that cannot possibly happen at the same time. If A and B are mutually exclusive, the probability of either A or B happening is PA plus PB. You had the probabilities here.
Like rolling a standard die and getting a 6 or getting an odd number, 1, 3, or 5. You can't do both on a single roll.
Perfect example. P6 is 16. P odd is 36. P6 OR odd equals 16 plus 36 equals 46 equals 23.
Or a customer choosing either the basic or the pro plan on a website, they can only pick one. Mutually exclusive choices.
Exactly. And related to this are complementary events. These are 2 mutually exclusive events that together cover all possible outcomes.
Like rolling a 6 versus not rolling a 6, or flipping heads versus flipping tails.
Right. Their probabilities must sum to 1 or 100%, so PA plus PA1. This leads to a really powerful shortcut. The probability of event A happening is PA equals PA. Sometimes it's easier to calculate the probability of A not happening and subtract from 1.
This rule seems incredibly useful for calculating the probability of complex events, like at least one of something happening.
Yes. The tower defense game example in the book shows exactly why. Suppose you have 5 defense towers, and each has an independent 20% or 0.2 chance of hitting an invader that passes by. What's the probability of stopping the invader, which means at least one tower hits?
Okay, my first instinct, maybe flawed, is just to add them up. Point 0.2 plus point 0.2 plus point 0.2 plus 0.2 plus point 0.2 plus point 0.2 plus 1.0. So 100% chance. Seems too easy.
It is too easy, and it's wrong. You can only add probabilities like that if the events are mutually exclusive, but here they're independent. It's possible that Tower 1 hits and Tower 3 hits. They aren't mutually exclusive.
Ah, right. So adding is incorrect. What do we do?
We use the complementary rule. What's the opposite of at least one tower hits?
The opposite would be none of them hit. All towers miss.
Exactly. At least one hit and all miss are complementary events. They cover all possibilities and can't happen together. So P, at least one hit, 1P, all miss.
Okay, that seems calculable. What's the probability of one tower missing?
If the hit chance is 0.2, the miss chance is 1.2, 0.8.
And since the towers operate independently,
The probability of all 5 missing is P miss.
P miss. So 0.8, 0.8 is being put 0.8, 0.8. That's 0.8 to the power of 5.
Right. And 0.85 is approximately 0.32768.
okay, so the chance of all towers missing is about 33%.
So now, using the complementary rule, the probability of stopping the invader, at least one hit, is 1P all miss, equals 1.32768.
Which is about 0.67232.
Roughly 67%, yeah. Not the 100% you might have guessed by incorrectly adding. That's a critical difference in assessing your defense. The complementary rule helped us get the correct answer.
That's a really powerful technique. The section also explicitly warns against the gambler's fallacy.
Oh, a classic. The incorrect belief that past outcomes in independent events influence future ones.
Like, if a fair coin lands on heads 10 times in a row, the next flip is somehow due to be tails.
Nope, the coin has no memory. The probability of tails on the next flip is still exactly 50-50, regardless of what happened before. Each flip is independent. Same goes for lottery numbers. Past winning numbers have no bearing on future drawings.
Our intuition really wants to find patterns, even where there aren't any.
It does. Formal probability helps keep us honest.
And finally, the book briefly touches on more advanced probability concepts like the binomial distribution.
Right, which you'd need for questions like, what's the chance of hiring exactly 7 people out of those 23 candidates? It gets more complex than the basics we covered.
But it points to tools like Wolfram Alpha that can help calculate these.
Yeah, it acknowledges that there's more to learn and resources are available. It's a good reminder that the basics are the starting point, but the field is vast.
Okay, so that wraps up the basics toolbox. We've covered powerful ways to model ideas with flowcharts and pseudocode.
Analyze conditions with logic and truth tables,
Count possibilities with multiplication, permutations, and combinations.
and understand uncertainty with basic probability rules. These are genuinely fundamental skills for problem solving, computational, or otherwise.
And as the book points out, understanding some of these concepts, especially the explosive growth we saw in counting possibilities with factorials or large combinations,
Yeah, those huge numbers.
is absolutely essential for understanding the next big topic, complexity. Why does the sheer number of operations or possible configurations matter so much when we think about computation? How fast do things get out of hand?
This transitions us directly into our deep dive on Chapter 2, complexity. The core question here is all about resources. How much time and memory does an algorithm actually consume as the problem size grows?
Right.
The book uses the simple analogy of sorting playing cards. Does sorting 52 cards take exactly twice as long as sorting 26? What about 1,000 decks? How does the effort scale?
And the answer isn't the simple linear scaling, usually. It depends entirely on the method you use the algorithm.
Exactly. The book defines an algorithm precisely. It's a method, a finite list of unambiguous instructions that is guaranteed to finish in a finite number of steps.
Okay, finite and unambiguous.
And we care deeply about the number of operations an algorithm performs because, simply put, fewer operations generally mean less computing time, less energy used, faster results.
But the number of operations usually isn't fixed. It depends on the size of the input problem, right? Like the number of cards to sort.
Correct. And as that input size grows, let's call the size and the number of operations can grow dramatically. This can lead to those bad surprises where a solution that works just fine for a small test case completely grinds to a halt for a large, real-world one.
Yeah, I've definitely hit that wall before.
That's where time complexity, often denoted as Tn, comes in. It's a mathematical function that describes the number of basic operations an algorithm performs as a function of the input size n.
The book calls this the running cost.
Right, so if sorting 26 cards takes T26 operations, how does T52 compare? If your sorting algorithm happens to have a time complexity that's roughly proportional to n squared, meaning Tn is approximately some constant c times n2.
Okay, Tn, Cn2?
Then what would T2n be? It would be approximately c times 2n2.
Which is C times 4n2.
Right. Or 4 times cn2, which is approximately 4 times Tn.
So for an N2 algorithm, doubling the input quadruples the time. That's not linear scaling at all.
Not at all. And that's a common complexity for simpler sorting algorithms. The book also highlights that Tn isn't always a single number for a given n. It can vary depending on the specific arrangement of the input data.
Okay, how so?
This leads to analyzing different cases. There's the best case, the minimum number of operations the algorithm might perform for size.
Like trying to sort a list that's already sorted? Maybe it's really fast then.
Exactly. Then there's the worst case, the maximum number of operations for size n. This often happens with, say, reverse sorted lists for sorting algorithms. This worst case is usually the most important one to consider because it gives you a guaranteed upper bound on performance. You know it won't take longer than this.
Okay, that's your safety net baseline.
And finally, there's the average case, which tries to capture the typical performance on random inputs. This can be harder to analyze mathematically, but is often relevant in practice. The book, and computer science in general, tends to focus heavily on understanding the worst-case complexity as a reliable measure.
So how do you actually figure out this Tn function for a specific algorithm? Do you just run it and time it?
Timing can give you empirical data, but the analytical approach is to examine the algorithm steps and count the basic operations it performs, assuming a hypothetical input size n. And again, you often focus on the worst-case scenario during this counting.
Okay, counting operations.
The book walks through this with a concrete example, the selection sort algorithm.
Okay, how does selection sort work again?
It works by repeatedly finding the minimal element from the unsorted part of the list and swapping it with the first element of that unsorted part. So, first pass finds the minimum of the whole list, swaps it to position 1. Second pass finds minimum of remaining list, position 2 onwards, swaps it to position 2, and so on.
Got it. It has loops, right?
Yes. It typically has an outer loop that runs n1 times, once for each position, except the very last one, which will be sorted by then. And inside that, there's an inner loop that scans the rest of the list to find the minimum element in the unsorted portion.
Okay, let's try to analyze the operations. The outer loop runs roughly n times. What happens inside it, besides the inner loop?
Inside the outer loop, but outside the inner loop, there are usually a couple of constant time operations, like maybe initializing a variable to keep track of the minimums index, and then performing the swap at the end of the pass. Let's say that's roughly 2 operations per pass. Since the outer loop runs n1 times, that's about 2 and 2 operations total from the outer loop structure itself.
Okay, something proportional to n. Now the inner loop, that's where the scanning happens. How many times does that run?
Well, it depends on which pass of the outer loop we're in. In the first pass, the inner loop scans n1 elements, comparing them to find the minimum. In the second pass, it scans n2 elements. In the third, n3, all the way down to the last pass where it scans just one element.
Ah, that sounds familiar. That's n1 plus n2 plus 1, 2. We just saw this sum in the counting section.
Exactly. We know that sum. Using Gauss's trick, the sum of numbers from 1 to n1 is n1 plus 1. 2 equals n1, n2. That simplifies to n2, n2.
Okay, so the inner loop runs a total of n2n, 2 times over the entire algorithm. What operations happen inside the inner loop on each iteration?
In the worst case, inside the inner loop, you might perform a comparison. Is this element smaller than the current minimum? And maybe an assignment. If it is, update the index of the minimum. Let's say that's roughly 2 basic operations per inner loop iteration.
Okay, so the total operations from the inner loop is about 2 n2, n2.
Roughly, yeah. Which simplifies to n2n operations.
So adding the outer loop part around 2n2 and the inner loop part around n2n.
The total Tn would be approximately 2n2 plus n2 plus n2. The source gives this Tn n2 plus n2 as a result for selection sort's time complexity.
So the dominant term is clearly n2.
Absolutely. Now let's connect this Tn n2 plus n2 back to how performance grows. The book suggests calculating the ratio T2n for different values of n.
Okay, let's try n8. T8, 82 plus 8, 2 plus 16. T16 is 162 plus 16, 2 plus 16, 2 plus 14 plus 14 plus 14. Because what's the ratio? 270, 70 is about 3.86.
Okay, close to 4, but not quite. Now try going from n16 to n32. T32 equals 322 plus 322 equals 1024 plus 30 equals 2584. The ratio T30, T16 is 1054 to 70. That's about 3.90.
It got closer to 4.
Exactly. This shows numerically that as n gets larger, the n2 term becomes much more important than the plus n or designed or 2 terms in determining how much longer the algorithm takes when you double the input. The ratio gets closer and closer to the ratio of the dominant terms, 2n2, n2 equals 4.
This leads directly to the critical concept of understanding growth based on the dominant term.
Yes, this is a huge realization in algorithm analysis. For very large inputs, which is often what we care about in computer science, the lower order terms, like the plus n and n2 plus n2, and any constant factors or terms, like the 9 to 2 or multiplicative constants we might have ignored in our rough counting, become insignificant compared to the term that grows the fastest.
The term with the highest power of n.
Exactly, that's the dominant term, and it dictates the algorithm's growth rate or scaling behavior for large as Rhine n.
So like with selection sorts Tn, n2 plus n2, the dominant term is n2. So for large n, Tn behaves like n2. We could say Tn is on the order of n2.
Precisely. The index cards example the book uses illustrates this perfectly. If sorting one box of n cards using an algorithm like selection sort, which behaves like n2, takes, say, 2 hours, how long will it take to sort 10 boxes, which is 10 n cards?
Well, if Tn behaves like n2, then T10 should behave like 10 n2.
What is 100 n2?
Right, so it will take about 100 times longer. If 2 hours was proportional to n2, then 100 times that is 200 hours, just for 10 times the cards.
Ouch. That's not great scaling.
Not at all. And even if another algorithm, like bubble sort, has a slightly different Tn function, say Tn equals 0.5 n2 plus 0.5 n.
Its dominant term is still n2. Well, 0.5 n2.
Right. When you compare the ratio T10 for bubble sort for large n, you'll get approximately 0.5 10n to 0.5 n.
The 0.5 cancels out. You still get 100 n2, n2 equals 100.
Exactly. The constant factor in front of the dominant term doesn't affect the scaling ratio for large inputs. Both algorithms scale quadratically. Both take about 100 times longer for 10 times the input.
The book's graphs must show this.
Yes, they beautifully illustrate how functions with the same dominant term, like n2, n2 plus n2, and 2.5 n2 plus 0.5 n, might look different for small n. Maybe one is consistently faster than the other. But as n gets very large, their curves essentially run parallel when plotted on the right scale. They all scale in fundamentally the same way.
But here's the crucial part the book emphasizes. Functions with different dominant terms like n linear, n2 quadratic, n3 cubics, or maybe 2n exponential.
Those never run parallel for large n. Their growth rates are fundamentally different. A quadratic function like n2 will always eventually grow much, much faster than a linear function like n, no matter what constant factors you start with.
And n3 will always leave n2 in the dust eventually.
And 2n will leave all polynomial functions like n, n2, n3, and 100 completely behind. The growth rates are in different leagues.
So understanding this dominant term allows you to predict how the algorithm's performance will scale with large inputs without needing the exact messy Tn formula with all the constants and lower terms.
That's the key insight. It gives you the big picture of scalability.
And that leads us directly to the big O notation, which is the standard way to formally talk about these growth classes, right?
Exactly. Big O, denoted O, is a special mathematical notation used to formally classify functions based on their dominant term's growth rate, typically focusing on the upper bound or worst-case scenario.
So when we say selection sort and bubble sort behave like n2 for large inputs, we say they have a time complexity of O(n)2, pronounced big O of n squared.
Correct. Or sometimes just O of n squared. Other common classes you'll hear constantly in computer science are O1, constant time. Amazing. O log n, logarithmic time. Very good. O(n), linear time. Good. O(n) log n. O log n time, very common for efficient sorting. O(n)2. Quadratic time, okay for small inputs, problematic for large.
Yeah.
O(n)3. Cubic time, getting slow quickly. O(2n). Exponential time, usually bad news for large inputs. O(n). Factorial time, definitely bad news.
Got it. So big O gives us a standard language to compare algorithms based on how their runtime scales.
Precisely. Using Big O is the industry standard for comparing algorithms and predicting their performance for large-scale problems. For instance, we saw selection sort and bubble sort are O(n)2, but much more efficient sorting algorithms exist, like merge sort or heap sort, which have a time complexity of O(n) log n.
Okay, O(n) log n versus O(n)2. Let's look at the practical impact again. We saw that for O(n)2, increasing the input size by 10x makes it roughly 100x slower.
Right. Now for O(n) log n, the scaling is much, much better. If you increase the input size by 10x, from n to 10n, the time increases by a factor of approximately 10n ln n log n.
That looks complicated.
It simplifies nicely for large n. Log 10 is log 10 plus log n. So the ratio is roughly 10n, log 10 plus log n. Log n equals 10, 1 plus log 10 log n. As n gets very large, log n grows, so log 10 gets small. The factor approaches 10 times something slightly larger than 1. The book calculates for a specific base that 10x input leads to about 34x cost for on log n, not 100x.
Okay, 34x is way better than 100x for a 10x increase in data.
Yeah.
And the difference must become truly staggering for very large inputs.
Absolutely. The book gives the example of n equals 1,106,000. For an ON2 algorithm, n2 is 1062 is 1012. That's a trillion operations. For an ON log n, log base 2 of a million is roughly 20. So n log n is roughly 1,020,000 20 million operations.
A trillion versus 20 million, that's astronomical.
It really is. That could easily be the difference between a computation taking years versus taking minutes or seconds. This is why understanding Big O is absolutely critical for choosing algorithms that will actually work for real-world large data sets. It helps you predict if an algorithm is even feasible for the scale of the problem you need to solve.
It's not just about shaving off a few milliseconds, it's about feasibility.
Often, yes. The book also mentions the gold standard O1 algorithms, constant time.
These take the same amount of time regardless of input size.
Pretty much. Like, checking if a number is even or odd just involves looking at the last bit, or doing a modulo 2 operation takes the same time whether the number is 10 or 10 trillion. Finding the first element in a list. Accessing an element in an array by its index. These are O1. Amazing efficiency when you can get it.
On the completely opposite end of the spectrum are exponentials, what the book chillingly labels the not runnable zone.
Yeah, that's where things get scary. These are algorithms with time complexity like O2n.
2 to the power of n, we saw 223 was already 8 million.
Exactly. 230 is over a billion. 240 is over a trillion. 260 is over a quintillion. It grows incredibly fast.
Faster than polynomials like n2 or n3.
Much, much faster. The book uses graphs to show just how brutally 2n dominates polynomial functions like n2 as n increases. You can zoom out and out, and the towing curve just goes almost vertical compared to the n2 curve, which looks practically flat in comparison for large n.
Even if you try to cheat by, say, multiplying n2 by a huge constant and dividing 2n by a huge constant.
Doesn't matter in the long run. For any polynomial length, no matter how large k is, and any exponential n where 1, the exponential function will always eventually overtake and dominate the polynomial function as n gets large enough, always.
So the implication is stark. Exponential algorithms, O2n or similar, are generally considered impractical or not runnable for any but the very smallest input sizes.
Pretty much. Even if you have the most cleverly optimized code running on the fastest supercomputer imaginable, the fundamental growth rate of the algorithm itself means it will quickly become overwhelmed as n grows even modestly. You can't brute force your way out of exponential complexity with hardware alone.
And algorithms with factorial time complexity, O'Hare, are even worse.
Oh, yes. Remember the traveling salesman problem? Trying to find the optimal solution by checking all n permutations is simply impossible for non-trivial numbers of cities.
So it's crucial to be able to recognize when a problem seems to demand exponential solution or falls into this not runnable class.
Definitely. These problems are often related to the famous class of NP-complete problems in computer science. Trying to find a guaranteed optimal solution for large inputs with an exponential algorithm is often, as the book puts it, fighting the impossible. Unless, as the book chicly mentions, you're hoping to win the Clay Mathematics Institute's $1 million prize for solving the P versus NP problem, basically proving whether these hard problems can be solved efficiently in polynomial time or not, a huge open question.
Right. Probably not the strategy for most projects.
Probably not.
Okay, so we've talked a lot about time complexity, but complexity isn't solely about time. Section 6 covers counting memory or space complexity.
That's right. Algorithms don't just take time, they also need space working storage in the computer's memory, RAM, to perform their operations. And memory, while vast these days, isn't infinite.
Especially on smaller devices or in shared environments.
Exactly. Space complexity measures the amount of working storage an algorithm needs. The analysis is very similar to time complexity. You look at how the memory requirements grow as the input size increases, and you express this using big O notation again.
Okay, so what's the space complexity of selection sort, for example?
Let's think. Selection sort mainly operates in place, just swapping elements within the original list. It needs a few extra variables. Maybe one to store the index of the current minimum found in the inner loop, maybe a temporary variable to help with the swap.
But the number of those extra variables doesn't depend on whether the list has 10 elements or 1,000,000, right?
Exactly. The amount of extra memory needed is fixed. It's constant. So selection sort has a space complexity of O1. Very memory efficient.
Okay. But not all algorithms are like that.
Definitely not. Many algorithms need space that does grow with input size. For example, an algorithm that needs to create a complete copy of the input list to work on would have ON space complexity. Some algorithms, maybe dealing with matrices or complex data structures, might even require ON2 space.
The book points out there are often trade-offs between time and space.
Yes, this is a classic consideration in algorithm design. Sometimes, because of strict memory limitations, you might be forced to choose an algorithm that's slower in terms of time complexity, say ON2 time, but uses very little extra memory space.
Over a faster algorithm, maybe ON log n time, that unfortunately requires significantly more working space, perhaps ON or even more.
You have to balance the resources, and the book hints that later chapters, particularly those on data structures, will show how clever ways of organizing and handling data can help manage and sometimes improve space complexity.
Makes sense. So to bring our deep dive into complexity to a close, we've learned that understanding how algorithms consume resources, both time and memory, as the problem size grows is absolutely fundamental.
We've seen how to analyze the number of operations, TN, how the dominant term predicts the growth rate for large inputs, and how Big O notation provides a standard language to classify algorithm efficiency and scalability.
We also saw why exponential growth is such a hard barrier for large problems, making some approaches fundamentally not runnable.
And the critical importance of considering space complexity and those potential time-space trade-offs.
This complexity analysis provides the answers to crucial questions you should ask about any solution. Will one algorithm be significantly faster than another for the same problem as the data grows? How will the runtime change if my input data doubles or triples or grows by a factor of 10?
Is this algorithm even practical or feasible for the scale of data I actually need to handle? Can simply optimizing my code or buying a faster computer realistically solve the performance problem if the underlying algorithm has, say, exponential complexity? Usually the answer is no.
Right. These first two chapters from Computer Science Distilled really provide the bedrock, don't they?
Absolutely. We started with the fundamental tools in the basics chapter, ways to break down problems, model ideas, precisely using flowcharts and pseudocode, handle logic rigorously, count possibilities accurately, and understand the basics of probability.
Then we moved into complexity to gain the critical ability to analyze how efficient those potential solutions actually are, especially as problems scale up. How much time will they take? How much memory? Will they even finish?
These are truly the essential first steps in developing that powerful computational thinking mindset. It's about structure, logic, and efficiency.
And that's a profound value of this book and this whole approach, really.
Yeah.
It distills these concepts, which might sound intimidating if you just see the jargon, into accessible forms. It empowers you to think computationally and use computers, and perhaps even your own time and resources, much more effectively.
So here's maybe a provocative thought for you, the listener, to carry forward and mull over. We've spent this time seeing how understanding computational thinking, the ability to break down problems, apply logic, count possibilities, analyze complexity is vital for computer science and programming. But how does this way of thinking apply to large-scale challenges in your own life or work that might have absolutely nothing to do with writing code? How does recognizing the potential for exponential growth in complexity, maybe the number of communication pathways in a growing team, or the number of dependencies in a huge project plan, how does recognizing that potential for nonlinear scaling change how you approach planning that huge event, organizing a massive amount of information, or managing a complex multi-dependent project? Can you spot the potential ON or O2N lurking in everyday plans?
That's a fascinating question, applying Big O thinking to life itself.
Kind of. It's about recognizing how things scale.
If you want to dive deeper into these concepts and explore the other fascinating chapters in the book on strategy, data, algorithms, databases, and more, you can find a full copy, digital or print.
Check the references provided in our sources. The book's website is mentioned there, specifically code.energycomputerscience distilled. Well worth checking out.